Hey guys, so when we go sailing, we could go from point A to point B with a paper chart and a sextant. But let's face it, these days 99% of us boaters rely on a chart plotter to help us navigate. And what is a chart plotter? Essentially, it's just a GPS with a bunch of additional functions to make maritime navigation easier. Now, I could navigate with our paper charts and binoculars, sure, but I'm a bit lazy. So today we're going to dive into the world of GPS navigation. We're first going to talk about how and when the GPS system was born, what are the three main segments of the GPS system, and how a bunch of satellites in space manage to calculate a position, how we can make sure that position is calculated correctly. This video is going to feature atomic clocks, groundbreaking special effects, and cheesy graphics, so I hope you enjoy it. GPS is the acronym for Global Positioning System, and it was first developed in the US in the 1970s, with the first satellite being launched in 1978. The system was primarily developed for the military, but in the 80s, civilian use was slowly rolled into operations. By 2000, the entire GPS system was open for global civilian use without any limitations, and nowadays, users from all over the world rely on GPS to function in their everyday lives. Now, GPS is the US system of GNSS, or Global Navigation Satellite System. And because it turned out to be quite useful, many developed nations have chosen to engineer and launch their own GPS systems. Europe has developed and launched its own system called Galileo, Russia, GLONASS, China, BeiDou. A few nations have developed more regional systems. India's has one called NAV-IC, and Japan has a regional system called QZSS. While all these systems have their differences, their general function is the same. So for the purposes of this video, we're going to focus on the American system, the world-famous GPS. At a high level, the GPS system has three segments: the space segment, the control segment, and the user segment, which really doesn't tell us much, so we're going to dive into each of those segments and get a better understanding of what they are and how they work together to tell us where we are and where we need to go. The space segment is called this way because, well, it's in space, and it consists of the satellites that the GPS needs to calculate and send position data. For GPS to work and provide global coverage, the system needs to have 24 functioning satellites. Conceptually, a user should be able to see 12 of these satellites at any time. However, obstacles such as terrain, buildings might obstruct the view of the sky and limit how many satellites we can see. These satellites are located about 10,000 nautical miles above the surface of the Earth and make around 2 orbits a day. While the system requires 24 satellites to work correctly at any time, there are about 30 satellites zipping around space and called upon in case of a failure to one of the primary satellites. On board the satellites is a bunch of equipment you would expect to find on a satellite, including thrusters, solar panels, computers, and other transmitting equipment. But each of those satellites also carries 4 atomic clocks. And I know what you're thinking when I tell you atomic clock, but it's not what you're thinking. We'll get back to that a little bit later down the road. The thing to remember about the space segment is that the satellites are sending signals to the user segment so that we can know where we are. It's important to understand, though, that the GPS signal is very, very weak. How weak, you ask? Well, imagine looking at a 25-watt light bulb from 10,000 miles away, and you'll get the picture, or rather, you might not get the picture. So, while the applications of GPS are very powerful, its actual signal strength is very low. The control segment is called that way because it monitors and communicates with the space segment. In the case of GPS, it is the US Space Force that is in charge of monitoring and controlling. So most of the control stations are located at the US Space Force installations. The master control station is located at Schriever Air Force Base in Colorado. This, along with a number of backup and ground monitoring stations around the world, make up the ground control network. The control segment monitors the orbits of the satellite, the state of the atomic clocks, and more generally, anything having to do with the satellite's health and proper functioning. So now let's look at the last segment. Us. The user segment, this is where you and I come in. The user segment consists of the millions upon millions of GPS receivers that are out there, from your phone to your chart plotter or even your watch. The important thing to remember here is that the user segment is simply receiving a signal from the GPS satellites and processing it. It is not communicating back to the satellites in any way. Now, how does this all work together? Now that we have an understanding of the three segments of the GPS system, let's have a look at exactly how they work together to calculate our position. To determine where someone is at any point in space, we need to know the user's latitude, longitude, and altitude. For sailors, altitude doesn't matter unless you're sailing between Gibraltar and the Canary Islands.
Oh God. Brace yourselves.
Joking aside, for airplanes, hikers, surveyors, all who operate at different altitudes, it's an important metric. To determine one's position, the GPS uses a concept called triangulation, whereby knowing the distance from 3 different satellites can determine our latitude, longitude, and when we're using 4 satellites, we can determine our position in 3D, including altitude. In principle, the system is relatively easy. We can determine our distance by measuring the amount of time it takes a signal to travel from the satellite to our GPS unit with the help of 3 pieces of data. First, the almanac data. My GPS receiving unit will have a general idea of where the satellite will be at any given time, which will give me a good indication of where the signal comes from. But for my GPS to calculate my exact position, it's going to need to know exactly where the satellite is, and thus we need ephemeris data. And that's where our atomic clock comes into play. We will see later how they work exactly, but for now we need to know that ephemeris data provides information on the atomic clock, or the exact time, and give us information on the satellite's exact position in space and its health. The third thing is the time at which the signal was sent, which is also given to us by the atomic clock. Based on all of this information, we can use a simple formula, d equals v times t, or distance equals velocity times time. Because the radio waves are coming from the satellite traveling at the speed of light, we already know that v is fixed at 3 times 10 to the 8th meters per second. Now we just need to measure the time between the moment the signal is sent by the satellite and received by the GPS unit. And that is why we need very, very accurate time data. If the timing is off by just a fraction of a second, it can throw our position way, way off. Because it would be way too expensive to put big, heavy atomic clocks on all our user devices, they're placed in the satellites. Now when the satellite sends the signal, it also sends time data to the GPS device. So based on how your device is programmed, the time on your GPS can be adjusted by the satellite's atomic clock. Yes, now you understand how the clock on your GPS gets its data from. Now that we have data on the distance between the satellite and the GPS, we can start to plot a location. At this point, all we know is the satellite's position in space and the distance from it. That could be anywhere on this circle around the satellite. If we bring in a second satellite and repeat the calculation process above and draw a distance circle around it, we have now narrowed our potential position to any point at which the 2 circles cross, which will be these 2 different points. Adding a third satellite and a circle around it will give us an exact location, longitude position. Remember though, this is only good if we're working at sea level or in 2D space. But most of us live in 3 dimensions, so the circles I have drawn are actually 3D spheres. To determine our 3D position, we'll actually need a 4th satellite, and boom, we have a position. Now, how do we know that the position is correct? It's important to understand that with 3 or 4 satellites in our view, our GPS receiver can tell us where we are, but there's no way for our system to tell us if the position is correct. Maybe one of the satellites is sending us some bad data or the timing is off. In GPS lingo, we call this integrity, the measure of trust or correctness we have in our information. Many GPS receivers, which are used for critical operations such as boats or planes, have a functionality called RAIN, or Receiver Autonomous Integrity Monitoring. RAIN, if it's working correctly, will ensure the signal is correct, and if it's not, it will provide an alert to the user. In order for RAIN to work, we need to have 1 additional satellite to the required 4 satellites for the position. The additional satellite allows the receiver to plot different positions using different 4 satellite combinations. One combination of 4 satellites may show us one position, while another combination of 4 satellites may give us a different location. The GPS device or the user can set a limit as to how close each of the positions given by the combination of satellites needs to be before you get an alert that the position shown could potentially be wrong. Further, some RAM receivers have the possibility to determine if a satellite is outside the limit set, which satellite is causing this problem, and eliminate it from the equation. And for this functionality, we need to receive a signal from 6 satellites. So to recap, to calculate an accurate position, we need 3 satellites to determine a 2D position, 4 satellites to determine a 3D position, 5 satellites to ensure the integrity of the signal that we have, and 6 satellites to determine if a satellite is bad and exclude it from the equation. Remember, in general, we should be able to see up to 12 satellites at any time, so having 6 satellites should not be a problem. However, the lower the satellite to the horizon, the more atmospheric interference may have, so potentially we can't use it. The same if we have obstructions such as mountains or buildings. With the signal being so weak, it just can't get through. So now, what can go wrong? No matter how advanced the system, there will always be issues with it. Most of the problems with GPS revolve around signal interference. Some of this might be intentional, such as spoofing or signal jamming, like in military zones, and some of it might be unintentional, such as atmospheric interference. Regardless of the source, it's important to understand some of these limitations and what can be done to, well, fix it. The atomic clock goes less atomic and more old pendulum clock. Clock errors come from a few sources. Because of the principle of relativity, which we will not get into in this video, the clocks in space will run slower than the clocks on the ground. For most people, this difference is unnoticeable. However, because the time aspect is so important, if we do not correct for this, it can throw the clocks off, thus giving us incorrect position. The control segment of the GPS system can identify these errors through their own atomic clocks on the ground and correct it. There could also be mechanical errors with the atomic clocks on board, which is one reason why there are 4 on each satellite. The Ephemeris data is just wrong. If the satellite location data, which is sent from the satellite to the GPS receiving device, is incorrect, it will also throw our position calculation off. We might have the correct distance, but if we don't know where the distance is from, it's useless. Again, another reason we have the control segment, watching our backs all the time. Signal bouncing, AKA Multipath. When using the GPS in urban or mountainous environments, the signal can bounce off the buildings or mountains, giving us bad readings and thus throwing your position off. And that is called multipath because it can take multiple paths. Unfortunately, there's not a lot we can do about this. Most cell phones use triangulation through cell phone towers to aid or assist your GPS position, but on a boat, this is rarely an issue for obvious reasons. Someone doesn't want you to know where you are, AKA spoofing or intentional jamming. It's not hard to see why some people might want to throw off a GPS signal. Even recently, there have been reports around airports where the GPS signal have been significantly off. Generally, this comes down to foreign states or bad actors who want to degrade the accuracy and integrity of the signal because they just don't want you to know where you are. This has devastating effects for us users, and let's face it, we can't do much about it. Only being aware that in certain areas, you are not always welcome to freely navigate. The atmosphere and the sun are playing tricks on you. As the GPS signal passes through the atmosphere, the ionosphere, and the troposphere, the signal path can get slightly distorted, which is called signal interference. When the path gets distorted, it takes a longer time for the signal to reach the user, and when this happens, it throws off our distance. Space weather, aka solar storms, can also cause such issues and even degrade the systems on board the satellites. Atmospheric interference always happens. The real question is how much and what we do about it. To counter this, most GNSS systems use a thing called augmentations, or as some people call it, differentials, to counter their effects. And you will ask me, what is GNSS augmentation? So now, my friend, this is the time we get very nerdy. At a high level, a GPS augmentation system uses a separate set of sensors to determine what the error is from ionospheric interference or space weather interference. After that error is determined, a correction is formulated and is sent out to user units, where it is applied to the internal algorithms and adjusts the position. There are three types of augmentation systems. Space-based. This is where the augmentation system is located, in space. Ground-based, again, located on the ground. And internal-based systems, such as gyro units found on aircraft or ships. Because the ground-based augmentation system isn't extremely developed yet, and internal-based systems are extremely expensive and heavy, we are going to focus on space-based augmentation systems, as they are the most developed and widespread. Space-based augmentation systems is commonly called SBAS. This is like GNSS in the US. Each country with a GPS system generally has its own SBAS. The US is called WAS, or Wide Area Augmentation System. Europe is called EGNOS, Russia SDCM, and China BD-SBAS. What is important to remember here is that most of these systems are not global, but regional and cover generally the areas around their state borders. So how does SBAS work? The system again uses the same three segments as the GPS system. For the space segment, 1, 2, or 3 satellites are located in geostationary orbit and are hardened to protect them from space weather events. These satellites are much further away and remain over the same point in space, which is the reason most of these systems are regional. The control segment again has a master control station, but is primarily built with a number of ground reference stations all over, in the case of WAS, the US. These ground reference stations are essentially GPS units, which, when installed, their exact positions are measured very, very accurately. When the normal GPS signal reaches the ground reference station, the signal will be off because of ionospheric interference, and that difference will be sent to the master control station, where a correction will be applied. Once that correction is applied, it is sent up to the WAS satellite and then down to your GPS unit, giving you an even more accurate position. But SBAS can also go wrong. While SBAS is very cool, it does have some limitations. First, the GPS device needs to have SBAS capability. Today, these systems are becoming more and more prevalent in everyday GPS devices, such as phones and chart plotters. However, it's still worth checking if the accuracy is critical to your operation. Second, if you are connected to an SBAS system outside the service area, the signal may actually hurt or degrade the accuracy and not help it at all. In this picture taken from a Ray Marine chart plotter on a boat in New Zealand, the GPS differential is turned on and is connected to the WAS system, which is in the US. You can see that the accuracy is 2.5 meters. However, if we turn off the GPS differential, we see the accuracy goes down to 0.3 meters, a massive improvement. In this case, the corrections being applied in North America would not be the same as the corrections needed to be applied in New Zealand. This is because ionospheric interference differs a lot depending on the latitude you are at. This chart gives you a rough idea of the different levels of interference at different latitudes. So how accurate are all these systems? Well, the stated accuracy for unaugmented GPS is around 13 meters 95% of the time. But with augmented GPS, the accuracy goes to 2 or 3 meters. Generally though, a user will see far greater accuracies than this. The military accuracy is far better than the civilian accuracy because the military has access to a few different sets of information which normal civilian users do not. GPS technology has revolutionized maritime navigation, making it possible for seafarers to get precise position data at any time and almost anywhere in the world. But with that said, Sailors have navigated the seven seas without GPS for hundreds of years, relying instead on dead reckoning, pilotage, and celestial navigation. So do you actually need a GPS on board? I'll let you answer that question in the comment section below. I hope you enjoyed this video, and if you did, give it a thumbs up, and if you enjoy nerdy talks about boat equipment, consider subscribing to our channel. If you want to support our video production, check out our Patreon page, but until next time, don't get lost. Bye-bye.